Hello viewers, welcome to online course on Mathematics 3. Today we are going to discuss about the partial differential equation and the series solution of ordinary differential equation. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID sanjay.vishwas@gnit.ac.in. So let's move on the next slide. And this is the fourth module of Mathematics 3. That means the partial differential equation and the series solution of ordinary differential equation. So in this module we will discuss about the basic concept of partial differential equation, and after that we will talk about the solution of the initial value and the boundary value partial differential equation by separation of variables, Laplace and Fourier transformation methods. Okay, so next we will talk about the introduction of the series solution of the ordinary differential equation, and then the fourth topic of the module 4, and it will be Bessel's equation. So we will discuss also the Bessel's equation and the legendary equations of a ordinary differential equations. So there are 5 topics on the partial differential equation and the series solution of ordinary differential equation. So today we are going to discuss about the basic concept of partial differential equations as well as the wave equation. We will discuss in this lecture. And after that we will talk about the Laplace and the Fourier transformation also, and the introduction of the series solution of the ordinary differential equation, and then we will talk about the Bessel's and legendary equations of the differential equations. Okay, let us move on the next slide. So there are some references of module 4, that means the partial differential equation and the series solution of ordinary differential equation. So you can take any one of the following books. So first you can take either Bronze Art differential equations, Shom outline series, okay, or you can take the differential equation by Ross, S.L. Ross. Otherwise you can take higher engineering mathematics or by Gravel, okay, or the partial differential equation by Prashad, okay, or you can take the elements of a partial differential equation by Schneider, or you can take the advanced engineering mathematics by Crazy E. So there are 6 references I have given in that slide. You can take any one of these 6 books, okay, for reference. After that let's move on the next slide. So this is my first lecture on the partial differential equation, that means the module 4, and this is actually the basic concept of partial differential equations. Okay, so here is the content of today's lecture. So first we introduce the partial differential equations, and after that we will discuss about the introduction to different method of solution of partial differential equations. Okay, so next we will talk about the separation of variables of partial differential equations, and then we will study on the one dimensional wave equation. This is a very important part of the partial differential equation, you know. Okay, and we can solve this wave equation by the separation method or separation of variables method. And after that we will talk about some related examples on the wave equations. Okay, first we will begin with the introduction to partial differential equation. So there is a change between the ordinary differential equation and the partial differential equation, where the partial differential equation are the derivative are the partial. Okay, that means if the function u is a function of x comma y, and if we differentiate this equation with respect to x, then y is constant. But in an ordinary differential equation, if we differentiate it with respect to x, then y is not a constant, y is also the variable. Okay. So in science and technology, often we face some problems involving the partial differential equations with constant coefficient. Okay, together with some boundary conditions as well. So we can solve the partial differential equation with the boundary condition, and these are known as the boundary value problem. Okay, so if the partial differential equation with boundary condition is called the boundary value problem. And in this chapter, we shall discuss some special type of partial differential equation known as the wave equation, heat equation, and the Laplace equation, and their solution by using the technique known as separation of variables. Okay, so the separation of variable is a very important part of partial differential equation, and in this chapter we will discuss about the wave equation, heat equation, and the Laplace equation. Okay. By the method of separation of variables. Here is the examples of some important partial differential equations, and this one is actually del 2u del t square is equal to c square into del 2u del x square, and this is called the one-dimensional wave equation. Move on the next equation. So del u del t is equal to c square into del 2u del x square. So this is called a one-dimensional heat equation. And del 2u del x square plus del 2u del y square is equal to 1 is called two-dimensional heat equation, or the two-dimensional Laplace equations. Okay, so in the first equation where u is a function of x comma t, and in the second one it is also the function of x comma t. So there are two variables x and t. But in the third problem where the function u is a function of x comma y. So these three equations are the wave equations, heat equations, and the Laplace equation, and we can solve this equation by the method of separations. Okay. So after that, we will introduce the different method of the solution of the partial differential equation. So let's start. A second order partial differential equation and a system of second order partial differential equations can usually be classified as parabolic, hyperbolic, or elliptic. Okay, so in a second order differential equation, the nature of are either parabolic is type, or hyperbolic, or the elliptic. So these classifications gives an intuitive insight into the behavior of the system itself. So the general second order partial differential equation is of the form a into uxx. So uxx means del 2 del x square plus 2 into b, and a, b, c are all the constant term, you know. So 2b into del 2u del x del y, this is the mixed order differentiation, partial differentiation, plus c into del 2u del y square. So this is the second order partial differential equation with respect to y and up to infinity, and this is equals to 0. And this is called the general second order partial differential equations. So just as one classifies conic section into parabolic. Okay, so from this we will get the solution of this general second order differential equation, and the conic section is either parabolic, hyperbolic, or elliptic, and it is based on the discriminant of the second order partial differential equation. So what is the discriminant of the second order partial differential equation? And it is actually b square minus 4ac. Okay, where b, a, and c are all constant term. Okay, so the discriminant b square minus 4ac, the same can be done for the second order partial differential equations. So there are three nature of the discriminant, and you know the nature of the discriminant are either is less than 0, or is greater than 0, or equals to 0. So if b square minus 4ac is less than 0, then the elliptic equation tends to smooth out any disturbances. A typical example is the Laplace equations, and the motion of the fluid at subsonic speed can be approximated with the elliptic partial differential equations. And if the discriminant b square minus 4ac is equals to 0, and from this we'll get the parabolic equation, and it tends to the smooth out any pre-existing disturbances into the data. And the typical example is the heat equation. Okay, and if b square minus 4 ac is greater than 0, and then we will get the hyperbolic equations and tends to the amplify any disturbances in the data. And that this is the typical examples in the wave equations. So when b square minus 4ac is less than 0, and from this we will get the elliptic conic, and the typical example is the heat equations. Okay, and if b square minus 4ac is equals to 0, we will get the Laplace equation, and if b square minus 4ac is equals to 0, then from this we will get the heat equation. And if b square minus 4ac is greater than 0, and from this we will get the conic, that means the hyperbolic, and from this we will get the wave equations. Okay, and the motion of the fluid at the supersonic speed can be approximated with hyperbolic partial differential equations. Okay, so the nature is depend on the discriminant of the second order partial differential equations. Okay, so this method is classification can easily be extended to system of partial differential equations by eliminating the eigenvalues of the coefficient matrix. Okay, so in this situation the classification scheme becomes either elliptic or parabolic or hyperbolic, and these are all the depend on the eigenvalue. Okay, so the equation or the conic section is a elliptic, then the eigenvalue are all positive or all negative, and it is equals to the parabolic, then the eigenvalue are all positive or all negative save one which is 0. Okay, and it is hyperbolic, then there is at least one negative and at least one positive eigenvalues, and none of the eigenvalues are 0. Okay, so and from this we will get the conic section, the conic of a second order partial differential equations, and they are either elliptic or parabolic or hyperbolic, and it all depend on the nature of the eigenvalues. Okay, and you know this is the nature. So all the eigenvalues are positive or negative, then we will get the elliptic conic, and if the eigenvalue are all positive or negative, and say one is a 0, at least one is 0, then it is a parabolic conic. Or if the eigenvalue at least one is negative or at least one is positive, then none of the eigenvalues are 0, then we will get the hyperbolic conic. So let us move on the next slide. So in this slide we will discuss about the method of separation of variables. Okay, so this is a very important part of the partial differential equation, you know, and from this we'll get the solution of the wave equations, Laplace equations, and the heat equations of the partial differential equation. So suppose the given partial differential equation involves two independent variables x and y and one dependent variable u. Okay, so in this method we assume the solution is of the form u of x comma y is equal to capital X of small x, capital Y of small y. So here capital X and capital Y are the function of x and y respectively. Okay, so where capital X is the function of small x and capital Y is the function of small y. Okay, so now substituting this into the given equation, that means the given partial differential equation, second order, we shall obtain two ordinary differential equation, one in each of the unknown function x and y. Okay, so then also the boundary conditions will be modified involving x and y separately, and after that solving two ordinary differential equations using the boundary conditions, we get two particular solution, and hence we obtain the most general solution of the given partial differential equations. So you know, in a separation of variables, we know u is the function of x and y, where x is a function of x and y is a function of y separately. And substituting this in the given equation, that means the partial differential equation, we will get two different differential equation, ordinary differential equation. Okay, and using the boundary condition, we will get to solution of the ordinary differential equation, and this solution are the particular solution. Okay, and now we multiply these two particular solution, and from this we will get the general solution of the partial differential equation. And we illustrate the method by the following examples. Okay, so here is the example how to solve the first order partial differential equation by using the method of separations or the separation of variables. Okay, so here is the problem. Solve by the method of separation of variable del u del x is equal to 4 into del u del y, where u of 0 comma y is equal to 8 into e to the power minus 3y. Okay, so the boundary condition is this, and this is the first order partial differential equation. Okay, so here is the solution of the given partial differential equation, and using the method of variation or separation method. So we will solve this given differential equation, that means partial differential equation with the boundary condition, and by the method of separation of variables. So here is the solution. So here u is a function of x comma y, so that u is equal to x of x into y of y. Okay, where x is a function of x only and y is a function of y only. So therefore del u del x. So if we differentiate it partially with respect to x, then from this we will get x dash into y. Okay, as well as del u del y is equal to x into y dash, where x is constant. Okay, so derivative of y is y dash. So now substituting in the given equation, we get x dash y is equal to 4 into x into y dash. So now from this equation we will get x dash by x is equal to 4 into y dash by y, and we can write this equation number 2, and this is equation number 1, u is equal to this. Okay, and this is the general solution. After find the value of x and y, we will get the general solution of u. So the left hand side of equation 2 is a function of x alone, and right hand side of equation 2 is a function of y alone. Okay, so they must be a constant, say lambda. So we will take a x dash by x is equal to lambda, as well as y dash 4 into y dash by y is equal to lambda. So from equation 2 we will get x dash by x is equal to lambda, as well as 4 into y dash by y is equal to lambda. And now we solve the two equations separately, and from this we will get the general solution. Okay, so from the first part we will get dx by x is equal to lambda into dx, and in the second one we will get dy by y is equal to 1 by 4 into lambda dy. Okay, so you know dx dash is equal to dx by dx. Okay, so now integrating these two equations, and from the first equation we get log of x is equal to lambda x plus log of c1. So where log of c1 is the arbitrary constant, and similarly we will get the solution of the second integration, and from this we will get log of y is equal to 1 by 4 into lambda into y plus log of c2. So where log of c2 is the integrating constant. So from the first equation we will get x is equal to value of x is equal to c1 into e to the power lambda x. Okay, where c1 is the integrating constant, and from the second equation we will get the value of y, and y is equal to c2 into e to the power 1 by 4 into lambda y. Okay, so these are the solutions of x and y, and after putting the value of the solution of x and y, we will get from equation y is the general solution. Okay, so from equation 1 we will get u is equal to c1 into c2 into e to the power lambda x into e to the power 1 by 4 into lambda of y, where x of x is equal to, that means x is equal to c1 e to the power lambda x, and y is equal to c2 e to the power 1 by 4 into lambda y. And this is the general solution, where c1 c2 is the integrating constant. So from this we will get the value of u, that means the general solution of u is equal to c1 c2 into e to the power lambda x plus 1 by 4 into lambda y. Put the boundary condition on the general solution, and after putting this one, that means u of 0 comma y is equal to 8 into e to the power minus 3y. That means when at x is equal to 0 and y is equal to 0, we will get u of 0 comma y, that means u of x comma y is equal to 8 into e to the power minus 3y. Okay, so after putting the value of the boundary conditions, and we will get from the general equation 8 into e to the power minus 3y is equal to c1 c2 into e to the power lambda into 0. So you know x is equal to 0. So lambda into 0 plus 1 by 4 into lambda into y. And from this we will get 8 into e to the power minus 3y is equal to c1 c2 e to the power 1 by 4 into lambda y. So now comparing this equation on both sides, we will get c1 c2 is equal to 8 and 1 by 4 into lambda is equal to minus 3. So from this we will get lambda is equal to minus 12 and c1 c2 is equal to 8. So therefore, after putting the boundary condition, we will get the general solution or the required solution, and it is u is equal to 8 into e to the power minus 12x plus 1 by 4 into minus 12y, where lambda is equal to minus 12 and c1 c2 is equal to 8. And after simplifying this, we will get u is equal to 8 into e to the power minus 12x minus 3 into y. So this is the required solution of the partial differential equation where the boundary condition is exist, and this is found by applying the separation of variable methods. After that, I will take one more examples on separation of variables. So here is the example, and this is the second example on the separation of variables. Using the method of separation of variables, solve the second order partial differential equation, that means del 2u del x square is equal to del u del t, where the boundary conditions are u of 0 comma t is equal to 0, u of 4 comma t is equal to 0, and u of x comma 0 is equal to sin 3x. Okay, so these are the boundary conditions of the partial differential equation. So we are going to find the general solution of u, and where u is a function of x comma t, by the method of the separation of variables. So here is the solution of the given problem. So let u is equal to x of x and t of t. Okay, so x of x is the function of x, and t of t, and this is the function of t on t, and u is the function of x and t. So therefore, the second order partial differential equation with respect to x, and it will be x double dash x into t. Okay, this is the second order partial differential equation with respect to x, where t is constant. And similarly, we will find the first order differential equation with respect to t, and it will be x into t dash, where x is a constant and t is a variable. Okay, so these two are the partial differential equation. So now substituting the given equation, we will get x double dash t is equal to x into t dash. Okay, where x double dash into t is equal to del t del x square, and x into t dash is equal to del u del t. Okay, so after putting the value of x del to u del x square and del u del t, we will get this one. Okay, and from this we will get x double dash by x is equal to t dash by t, and we can write this equation number 1. So the left hand side of equation 1 is the function of x alone, and the right hand side of equation 1 is a function of t alone. So they must be a constant, say minus lambda square, for fitting the boundary conditions. Okay, so therefore from equation 1 we will get x double dash by x is equal to minus lambda square, and t dash by t is equal to minus lambda square. Okay, so therefore from these two equations we will get x double dash plus lambda square into x is equal to 0, and dt by t is equal to minus lambda square into dt. Okay, so from equation 1, this is the second order differential equation of x. So from this equation we will get the general solution. So the auxiliary equation of this differential equation is m square plus lambda square is equal to 0. So from this we'll get m is equal to plus minus I into lambda. So that is the root of the auxiliary equation are imaginary. Therefore the complementary function is c1 into cos lambda plus c2 into sin lambda, you know. Okay, and the particular integral is 0. So in that case, if we apply the d operator method, we will get the solution. So the complementary function is the general solution of the first equation. Okay, so the x of x is equal to, this is the general solution of x, and it is equals to c1 cos lambda x plus c2 sin lambda x. Okay, and we can write equation number 2. And from the third equation we will get t of t is equal to c3 into e to the power minus lambda square into t. So if we integrate both sides, then from this we will get this one. Okay, so log of t is equal to minus lambda square t plus log of c2. So log of c3. So from this we will get t of t is equal to c3 into e to the power minus lambda square t, and we can write it equation number 3. So we are given u of 0 comma t is equal to 0. So this is the boundary conditions of the given problem. So u of 0 comma t is equal to 0. So from the given equation we will get x of 0 is into t of t is equal to 0. So this implies x of 0 is equal to 0, and this equation number 4. And also we have u of 4 comma t is equal to 0. That means, and you know u of 4 comma t, where u of x comma t is equal to x of x into t of t. So x of 4 into t of t is equal to 0, and from this we will get x of 4 is equal to 0, where t of t is not equal to 0. So from, and we can write this equation number 5. So using 4, and we get from equation 2 will get the constant value c1 is equal to 0, and therefore x of x, this equation, that means from equation 2 we will get x of x is equal to c2 into sin lambda t. Again using 5, and from this we will get and from the equation 5 we will get this one, that means c2 of sin lambda x, that means where x is equal to 4, that means c2 into sin 4 lambda is equal to 0. So using the fifth equation, and from this equation 2 we will get c2 into sin lambda, that means 4 lambda is equal to 0. And from this where c2 is the constant term, so this implies sin 4 lambda is equal to 0. Okay, and you know sin 4 lambda is equal to sin n pi, so which implies lambda is an integer. So therefore the general solution of the given partial differential equation is u of x comma t is equal to c2 into sin lambda x into c3 into e to the power minus lambda square t. And c2 and c3 are the constants, so we will take c is equal to c2 into c3. Then this general equation is reduced to c into sin lambda x into e to the power minus lambda square t. Okay, now we apply the third boundary condition, that means u of x comma 0, and this is equals to, from this we will get c into e sin of lambda x, where e to the power 0 is equal to 1. So as we are given u of x comma 0 is equal to sin of 3x, so therefore c into sin lambda x is equal to sin 3x, and from this we will get the two constant values, that means c is equal to 1 and lambda is equal to 3. So thus the required solution of the given partial differential equation, and it will be u of x comma t is equal to sin 3x into e to the power minus 9t, by applying the boundary conditions of the partial differential equation. Okay, this is the required solution or the general solution of the given partial differential equation. Now we are move on the next part of the partial differential equation. So this is the one dimensional wave equation. Okay, so there are three basic parts of the partial differential equation. You know, the first one is a one dimensional wave equation, second one is one dimensional heat equation, and third one is two dimensional heat equation or the Laplace equation. So we are going to find the three different equations, partial differential equation, by using the method of separations. So here is the one-dimensional wave equation. So this is the basically. So there are several approaches to solve the wave equations. The first one we will work with using the technique called separation of variables. Again, demonstrate one of the most widely used solution technique for partial differential equations. Okay. So in that section we will discuss about the wave equation, one dimensional, and how to solve the wave equation by using the separation of variables. Okay. So the idea behind it is to split off the original partial differential equation into the series of simple ordinary differential equation, each of which we should be able to solve readily using tricks already learned. Okay, so how to solve the partial differential equation by using the separation of variables? I have already learned this part. So the second technique, which we'll be seeing in the next section, and uses a transformations trick that also reduce to a complexity of the original partial differential equations, but in a very different manner. So this is the second solution is due to D'Alembert's and is called the D'Alembert solution as a result. So one dimensional wave equation you can solve the two different methods. So first we will take the method of separation, and I have already learned this part, and the second method it will be the transformations. Okay, either you can use the Laplace transformation or the Fourier transformation, and from this we will get the solution of the partial differential equation as well. So this second solution is due to the D'Alembert's, and this is called the D'Alembert solution. Okay. So the first note is that for a specific wave equation, in addition to the actual partial differential equation, we will also have boundary conditions arising from the fact that the endpoint of the string are attached solidly at the left end of the string. So therefore, when x is equal to 0 and at the other end of the string, which we suppose has overall length is L. Okay. So let's start the process by solving the partial differential equation by first figuring out that this boundary conditions implies for the solutions of functions. So we to start the separation of the variables technique, we make the key assumptions that whatever the solution function is. Okay, so that is we can write the as a product of the two independent functions. U if the U is a function of x and t, then where x is a function of x as well as t is a function of t. So each one of the which depend on just one of the two variables x or t. Thus imagine that the solution function u of x comma t, this is the solution of the given partial differential equations and can be written as x of x into t of t. Okay, and x is the function when x is the one end is point is x0 and the other end is equal to the overall length is same, so other end is L. So that is x lies in the interval 0 comma L. Okay, in that section. So the solution, this is the solution of the wave equations, or how to solve the wave equation by using the method of separations. So here let u of x comma t is equal to x of x and t of t, and we can write this equation number 1. And be the solution of the wave equation. This is called the wave equation. I have already learned. So del to u del t square is equal to c square into del to u del x square, and we can write it equation number 2. So where x is a function of x alone and t is a function of t alone. Okay. So therefore, the second order differentiation with respect to t, and from this equation 1 will get x into t double dashed, and del to u del x square. This is the second order differentiation with respect to x, and it will be x double dashed. That means the second order differentiation of x into t. And therefore from equation 2, after putting the value of x del to u del t square and del to del x square, then from equation 2 we'll get x into t double dash is equal to c square into x double dash into t. And now separate this equation, x double dash by x is equal to 1 by c square into t double dash by t, and we can write it equation number 3. So as left hand side of equation 3 is a function of x only, and the right hand side of the equation 1 is a function of t only. So they must be equal to a constant, say lambda, and I have already learned in the method of separation. Okay, where the left side is a function of x and the right side is a function of t, then we can write it as a constant and say lambda. So therefore from equation 3 we get x double dash by x is equal to lambda, that means x double dash minus lambda into x is equal to 0, and we can write it equation number 4, and from equation 3 1 by c square into t double dash by t, and it is equals to lambda, and from this we will get t double dash minus lambda c square into t is equal to 0, and we can write it equation number 5. So now we are going to find the solution of equation 4 as well as equation 5, and equation 4 and 5 are the ordinary differential equation, okay, second order. And from these two equations we will get the general solution of x and the general solution of t as well, and these two solutions are dependent lambda. That means the three cases arise according to lambda are 0, positive or negative, and if we lambda is 0 then we get the solution, okay, and this solution is when we put lambda is equal to 0 we get a solution, as well as when we put lambda is greater than 0 and lambda is less than 0 we'll get the different solution, okay. That means the solutions of equation 4 and 5 are dependent on lambda. So there are three cases arise according to lambda. So first case, when let lambda is equal to 0. Then solution of 4 and 5 are, when lambda is equal to 0 then x double dash is equal to 0 and t double dash is equal to 0. So therefore x double dash is equal to 0, that means x is equal to a1x plus a2, where a1 and a2 are the constant, and t double dash is equal to 0, and from this we will get t is equal to a3t plus t a4, where t3 and a4 and a3 are the constant, okay. So these two are the solutions when lambda is equal to 0. And after that, this is the case number 2, when lambda is positive, that means say lambda is equal to p square. So therefore from equation 4 and 5, and it will become respectively x double dash minus p square into x is equal to 0 and t double dash minus p square into c square into t is equal to 0. And after solving these two equations, so you can apply the d operator methods in that problem. So x double dash minus p square x is the second order differential equation, not a differential equation, okay. And you have learned these two parts in the first year or the semester 2 also. So the solution of this differential equation we obtained x is equal to b1 into e to the power px plus b2 into e to the power minus px. So the auxiliary equation of the first equation, it will be m square minus p square is equal to 0. Therefore from this we will get m is equal to plus minus p. So the two roots are the real and unequal. So therefore the complementary function is b1 e to the power px plus b2 e to the power minus px, and the particular integral is 0, where the right hand side is 0. So therefore the complementary function is the general solution of x. So therefore the solution of the first equation, it will be x b1 e to the power px plus b2 e to the power minus px. And similar thing will happen in the second part, not the second equation, and from this we will get the general solution. It will be b3 into e to the power pct plus b4 into e to the power minus p into c into t, where p into c is constant. So these two are the general solutions of equation 4 and equation 5 when lambda is positive, that means lambda is equal to p square, okay, where b1, b2, b3, b4 are the constant. And the third case, it will be when lambda is negative, that means minus p square. Then from equation 4 and 5 becomes respectively x double dash plus p square into x is equal to 0 and t double dash plus p square into c square into t is equal to 0. So these two are the respective equations when lambda is less than 0. So the auxiliary equation of the first differential equation, it will be m square plus p square is equal to 0. That means m is equal to plus minus I into p. So the roots of the auxiliary equation are the imaginary. Okay, and the complementary function, you know, c1 into cos px plus c2 into sin px, and the particular integral is 0. Why it is 0? Because the right hand side of this equation is 0. So therefore the general solution of x is the complementary function. That's why the general solution of the first equation, it will be c1 cos px plus c2 sin px. And similarly we can find the general solution of the second equation, and similar thing will happen in the second part also. So where t is equal to c3 into cos pct plus c4 into sin pct. Okay, where p and c are the constant, and c1, c2, c3, c4 are all constants. So therefore the various possible solution of the wave equations are, so in, you know, the wave, there are three types of equations in the given wave equations, and it is depend on the value of lambda. So the first solution of the given partial differential equation, that means the one dimensional wave equation, it will be a1x plus a2 into a3x t plus a4. Okay, and then we can write as equation number 6. Or it will be u of x comma t is equal to b1 of e to the power px plus b2 of e to the power minus px into b3 of e to the power pct plus b4 of e to the power minus pct. Okay, and we can write it equation number 7. And that this is the solution when the lambda is less than 0, and when the lambda is greater than 0. And in the third last one, the general solution of u comma xt is c1 cos px plus c2 sin px into c3 cos pct plus c4 sin pct, and we can write it equation number 8. Okay, so there are three possibilities for the wave equations, or the solution of the wave equations. Okay, and it depends on the p. And the first equation, you know, when lambda is equal to 0. Second equation will be found when lambda is greater than 0, and third equation will be found when lambda is less than 0. Okay, so these three are the solution of the given one dimensional wave equations. So one of this solution, we have to choose the solution which is consistent with the physical nature of the problem. So as we deal with the problem on vibration, u of x comma t must be periodic function, hence the solution given by 8 is the only suitable solution. So in the previous, so therefore there are three solutions, but the suitable solution, it is equation number 8. So this equation is a periodic equation. Okay, so therefore the equation 8 is the suitable solution. So now applying the boundary condition, that is u of x comma t is equal to 0 at x is equal to 0 and x is equal to L. Then from equation 8 we will get 0 is equal to c1 into cos pct into c3 plus c4 into sin pct, and from this we will get c1 is equal to 0. And if we put x is equal to L, then from this equation we will get 0 is equal to c1 cos pl plus c2 sin pl into c3 cos pct plus c4 sin pct. Okay, so from this we will get c1 cos pl plus c2 sin pl is equal to 0. That means c2, where c1 is 0, you know, so c2 into sin pl is equal to 0. That means pl is equal to n pi, where n is equal to 1, 2, 3 and up to infinity. Okay. So from this we will get p is equal to n pi by L. So now from equation 8 we get u of x comma t is equal to c2 into sin n pi x by L into c3 into cos n pi ct by L plus c4 into sin n pi ct by L. So that means after multiplying by this equation, this term, we will get cn into cos n pi c t L by L plus dn into sin n pi ct by L into sin n pi x by L for n is equal to 1 to 3 up to infinity, where Cn is equal to C2 into C3, this is the constant also, and Dn is equal to C2 into C4, this is also the constant. So thus for the different value of n, we consider the most general form of the solution as u of x comma t, and this is equals to summation over I is equal to 1 to infinity Cn into cos n pi ct by L plus Dn into sin n pi ct by L into sin n pi by L, and this is equation number 9, where Cn and Dn can be obtained using the initial conditions. Okay, so this is the general solution or the suitable solution for the given one-dimensional wave equation, for the boundary conditions are given. Now applying this derivation of one-dimensional wave equation, we will find the solution of the given problem. So here is the problem: solve the wave equation del 2u del t square is equal to c square into del 2u del x square. Given that u of 0 comma t is equal to 0, u of x comma 0 is equal to function of x, and the first derivative of u with respect to t, that is del u del t of x comma 0 is equal to 0, and x is lies in the interval 0 comma l. Okay, so we have from equation 9, in the I have already found the solution of this equation. Okay, so this is the equation. Okay, this is the general solution of the given equations. So u of x comma t is equal to summation over I is equal to 1 to infinity Cn into cos n pi ct by L plus Dn into sin n pi ct by L into sin n pi x by L. So this is the general solution or the suitable solution for the given partial differential equation, where the boundary conditions are given. Okay, so there x is lies in that interval, so the boundary condition is x is equal to 0 and x is equal to L, where u of x comma t is 0. Okay, in that boundary on the end point of x, that means that x is equal to 0 and x is equal to L. So therefore now from equation 9, that means this one will get the first differentiation with respect to t, and it will be summation over I is equal to 1 to infinity n pi c by a into minus of, so derivative of cos function is minus sin function, so minus Cn into sin n pi ct by L, okay, into n pi c by L, plus Dn into cos n pi ct by L, where Dn sin derivative of sin function is the cos function, so cos of n pi ct by L into n pi c by L into sin n pi by L. So from this, now we apply the initial condition, that means u of x comma 0 is equal to function of x, and del u del t of x comma 0 is equal to 0, and then from the above equation we get fx is equal to summation over I is equal to 1 to infinity. So when you put x is equal to x and t is equal to 0, in that equation we will get t is equal to 0, that means sin 0 is 0, cos 0 is 1, okay, and this one is 0. So that means this is equals to sin n pi x by a. This is actually the value of this is 1, okay, and that is n pi c by L into dn is equal to sin n pi x by L, and this Cn is a constant. So from this we will get the functional value of x is equal to summation over I is equal to 1 to infinity Cn into sin n pi x by L, and we can write it equation number 10. And if we put the second initial condition, then from the last equation we will get 0 is equal to summation over I is equal to 1 to infinity dn into n pi c by L into sin n pi x by L, and we can write it equation number 11. Okay, so therefore from equation 10, and equation 10 is represent the Fourier series of the function fx, and we have Cn is equal to 2 by L integration over 0 to L fx into sin n pi x by L into dx, and we can write it equation number 12. Okay, And from equation 11 we have dn is equal to 0 for all n. So therefore the general solution of the given partial differential equation, and it will be u of x comma t is equal to summation over I is equal to 1 to infinity cn into cos n by ct by l into sin n by x by l, while cn is given by equation 12, where cn is the represent the Fourier series of the function fx, and it is 2 by l into integration over 0 to l fx into sin n by x by l into dx. Okay, so I'll stop here today's lecture. Thank you.